A pin diode is a diode with a wide, undoped intrinsic semiconductor region between a p-type semiconductor and an n-type semiconductor region. The p-type and n-type regions are typically heavily doped because they are used for ohmic contacts. The wide intrinsic region is in contrast to an ordinary PN diode. The wide intrinsic region makes the pin diode an inferior rectifier, but it makes the pin diode suitable for attenuators, fast switches, photodetectors, and high-voltage power electronics applications. Operation. A pin diode operates under what is known as high-level injection. In other words, the intrinsic I region is flooded with charge carriers from the P and N regions. Its function can be likened to filling up a water bucket with a hole on the side. Once the water reaches the hole's level, it will begin to pour out. Similarly, the diode will conduct current once the flooded electrons and holes reach an equilibrium point, where the number of electrons is equal to the number of holes in the intrinsic region. When the diode is forward biased, the injected carrier concentration is typically several orders of magnitude higher than the intrinsic level carrier concentration. Due to this high-level injection, which in turn is due to the depletion process, the electric field extends deeply into the region. This electric field helps in speeding up of the transport of charge carriers from P to N region, which results in faster operation of the diode, making it a suitable device for high-frequency operations. Characteristics. A pin diode obeys the standard diode equation for low-frequency signals. At higher frequencies, the diode looks like an almost perfect resistor. There is a lot of stored charge in the intrinsic region. At low frequencies, the charge can be removed and the diode turns off. At higher frequencies, there is not enough time to remove the charge, so the diode never turns off. The pin diode has a poor reverse recovery time. The high-frequency resistance is inversely proportional to the DC bias current through the diode. A pin diode, suitably biased, therefore acts as a variable resistor. This high-frequency resistance may vary over a wide range. The wide intrinsic region also means the diode will have a low capacitance when reverse biased. In a pin diode, the depletion region exists almost completely within the intrinsic region. This depletion region is much larger than in a PN diode, and almost constant size, independent of the reverse bias applied to the diode. This increases the volume where electron-hole pairs can be generated by an incident photon. Some photodetector devices, such as pin photodiodes and phototransistors, use a pin junction in the construction. The diode design has some design trade-offs. Increasing the dimensions of the intrinsic region allows the diode to look like a resistor at lower frequencies. It adversely affects the time needed to turn off the diode and its shunt capacitance. Pin diodes will be tailored for a particular use. Applications. Pin diodes are useful as RF switches, attenuators, photodetectors, and phase shifters. RF and microwave switches under zero or reverse bias. A pin diode has a low capacitance. The low capacitance will not pass much of an RF signal. Under a forward bias of 1 mA, a typical pin diode will have an RF resistance of about 1 ohm, making it a good RF conductor. Consequently, the pin diode makes a good RF switch. Although RF relays can be used as switches, they switch very slowly. A pin diode switch can switch much more quickly. The capacitance of an off-discrete pin diode might be 1 picofarad. At 320 MHz, the reactance of 1 picofarad is about J500 ohms. As a series element in a 50-ohm system, the off-state attenuation would be -20 times the base 10 log of the ratio of the load impedance to the sum of load, diode and source impedances, or roughly 20 decibels, which may not be adequate. In applications where higher isolation is needed, both shunt and series elements may be used, with the shunt diodes biased in complementary fashion to the series elements. Adding shunt elements effectively reduces the source and load impedances, reducing the impedance ratio and increasing the off-state attenuation. However, in addition to the added complexity, the on-state attenuation is increased due to the series resistance of the on-state blocking element and the capacitance of the off-state shunt elements. Pin diode switches are used not only for signal selection, but they are also used for component selection. For example, some low-phase noise oscillators use pin diodes to range switch inductors, RF and microwave variable attenuators. By changing the bias current through a pin diode, it is possible to quickly change the RF resistance. At high frequencies, the pin diode appears as a resistor whose resistance is an inverse function of its forward current. Consequently, pin diode can be used in some variable attenuator designs as amplitude modulators or output leveling circuits. Pin diodes might be used, for example, as the bridge and shunt resistors in a bridge-T attenuator. Another common approach is to use pin diodes as terminations connected to the 0° and -90° ports of a quadrature hybrid. The signal to be attenuated is applied to the input port, and the attenuated result is taken from the isolation port. The advantages of this approach over the bridge-T and pi approaches are complementary. Pin diode bias drives are not needed, the same bias is applied to both diodes, and the loss in the attenuator equals the return loss of the terminations, which can be varied over a very wide range. Limiters. Pin diodes are sometimes used as input protection devices for high-frequency test probes. If the input signal is within range, the pin diode has little impact as a small capacitance. If the signal is large, then the pin diode starts to conduct and becomes a resistor that shunts most of the signal to ground. Photodetector and photovoltaic cell. The pin photodiode was invented by Georg Wiora and his colleagues in 1950. Pin photodiodes are used in fiber optic network cards and switches. As a photodetector, the pin diode is reverse biased. Under reverse bias, the diode ordinarily does not conduct. When a photon of sufficient energy enters the depletion region of the diode, it creates an electron-hole pair. The reverse bias field sweeps the carriers out of the region, creating a current. Some detectors can use avalanche multiplication. The same mechanism applies to the pin structure, or PIN junction, of a solar cell. In this case, the advantage of using a pin structure over conventional semiconductor PN junction is the better long-wavelength response of the former. In case of long-wavelength irradiation, photons penetrate deep into the cell, but only those electron-hole pairs generated in and near the depletion region contribute to current generation. The depletion region of a pin structure extends across the intrinsic region, deep into the device. This wider depletion width enables electron-hole pair generation deep within the device. This increases the quantum efficiency of the cell. Commercially available pin photodiodes have quantum efficiencies above 80 to 90% in the telecom wavelength range, and are typically made of germanium or InGaAs. They feature fast response times, running into several tens of gigahertz, making them ideal for high-speed optical telecommunication applications. Similarly, silicon PIN photodiodes have even higher quantum efficiencies, but can only detect wavelengths below the band gap of silicon, i.e., ~1100 nanometers. Typically, amorphous silicon thin film cells use pin structures. On the other hand, CDTE cells use NIP structure, a variation of the pin structure. In a NIP structure, an intrinsic CDTE layer is sandwiched by undoped CDs and p-doped ZNTE. The photons are incident on the undoped layer, and like a pin diode, a pin photodiode can also detect X-ray and gamma-ray photons. Example diodes: SFH203 or BPW43 are cheap general-purpose pin diodes in 5 mm clear plastic case with bandwidth over 100 MHz. They are used in RONJA telecommunication systems and other circuitry applications.